Students, up to now we see about the first 4 units of our DC machines and transformer subject. So what are those first 4 units? The first unit is electromechanical energy conversion and magnetic materials, and the second unit is DC generators, and the third unit is DC motors, and the fourth unit is single phase transformers. So from this video onwards we will see about the our fifth unit, which is nothing but three phase transformers. So coming to the syllabus of our three phase transformers, the contents is three phase transformer construction, types of connections and their comparative features, phase conversion, Scott connection, tap changing transformers, no load and on load tap changing of the transformers, three winding transformers, and the cooling of the transformers. So these are the contents in the unit 5. So coming to our class, so first we discuss about the three phase transformer constructions only. So under the three phase transformers, a three phase transformer is normally used to generate and transmit the electrical power. So the three phase voltages are raised or lowered by means of a three phase transformers. So the three phase transformers basically constructed in two ways. What are those two ways? By suitably connecting a bank of the three phase three single phase transformers, and by connecting a three phase transformer on a common magnetic structure. So whatever the case we consider, we can go for the four types of connections. What are those four types of connections? Means star star connection, and delta delta connection, and star delta connection, and delta star connection. So first we study about the bank of single phase transformers. So under that, three single units are connected in either in star connection or in delta connection. So in the figure shows the star delta connection of a three phase transformer. So here we have three transformers. So this is the transformer 1, and this is the transformer 2, and this is the transformer 3. So in this, the primary winding of the transformers are connected in star connection, whereas the secondary winding of the transformers are connected in delta connection. How we said that? By seeing this diagram itself, the primary winding is connected in the star and the secondary winding is connected in the delta means. So in star, there will be every transformer we have phase terminal and a neutral terminal. So this is the phase for the transformer 1, and this is the neutral for the transformer 1, and similarly this is the phase for the transformer 2, and this is the neutral for the transformer 2, and similarly this is the phase for the transformer 3, and this is the neutral for the transformer 3. So the neutrals of these three transformers are connected to one point, then that connection is called the star connection. And similarly here, the neutral of the first transformer is connected to the phase of the next transformer, and the neutral of the second transformer is connected to the phase of the third transformer, and the neutral of the third transformer is connected to the phase of the first transformer. Then such type of connection is called as delta connection. So the primary is connected in the star connection and the secondary is connected in the delta connection. So the diagonal representation also here we represent. So this is the star connected primary and this is the delta connected secondary. So in this case, since we use the three single phase transformers, if any case one is fault, then that fault can be replaced. But in case of the single unit three phase transformer, if the fault occurs, we cannot do anything. The whole unit is rendered useless. So this is the advantage of the three single phase transformers connected as a one bank. And similarly, the next slide explains the single unit of the three phase transformer. Single unit of the three phase transformer. So a three phase transformer can be constructed having 3 primary and 3 secondary windings on a common magnetic core. So in the previous, for the 3 transformers, we have 3 separate cores. But in this case, for the 3 transformer windings, that means 3 primary windings, and for the 3 secondary windings, we have only single core. We have only single core. So these are also normally classified into two types: 3 limbed core type transformer and 5 limbed shell type transformer. 3 limbed core type transformer and 5 limbed shell type transformer. So the 3 limbed core type transformer is nothing but the operation of the 3 limbed core type transformer is same as that of the core type of transformer in case of the single phase transformer. And similarly, the 5 limbed shell type transformer operation is similar to that of the shell type transformer in single phase transformer. So first we go through the 3 limbed core type transformer. 3 limbed core type transformer. So in this we have so many advantages. So here the core is, first we go through the diagram. So this is the 3 limbed, since we have the 3 limbs. Since we have the 3 limbs, this is the 3 limbed core type transformer, and here core is surrounded by winding on all sides. So here we have 3 sides: first side, second slide, and the third slide. For every slide we have the copper winding. That means here core is surrounded by winding on all sides. And next one is all limbs have equal cross section area. The cross section area of these all limbs are equal. And next is it has the less mechanical support. There is no mechanical support for the outer copper windings, where transferring this type of transformers, because of the some forces at the outside, sometimes the winding may be damaged. That means the mechanical support provided to this type of 3 limbed core type transformer is very less support. And the copper requirement is also more. Why? Because here the operation of the 3 limbed core type transformer is same as the single phase core type transformer. So there what we do, we can make the LV winding and HV winding on every limb. First we provide the LV winding, and then we can provide the HV winding. So first, this is the core of the transformer. The three limbs are the first core of the transformer. On that we provide the insulation for the low voltage winding. Then we provide the low voltage winding, and then insulation for the high voltage winding, and then we connect the high voltage winding. So as the winding increases, that means if you go for the high voltage winding, the area or the diameter of the limb will be increases. So as a result, the length of the conductor used is also increases. So the copper requirement is more, and similarly the insulation requirement is less. So we can provide a less insulation for providing the insulation between the core to low voltage winding and low voltage winding to high voltage winding. And next, it is used for high voltage rating and low current rating. So in the previous also, the core type are used for the high voltage rating and the low current rating. So in a similar fashion, the 3 limbed core type transformer is used for the high voltage rating and low current rating. So there is a, since there is no closed path here, so the flow of the flux, so third harmonic flux is absent. There is no closed path for the flow of the flux, so the third harmonic flux is absent. Since the third harmonic is absent, the flux and EMF produced is sinusoidal. So here the generated flux will be flows inside the core only. So there is no extra path for the developed flux. So since there is no extra path, then there is no talk about the third harmonics means while drawing the magnetizing current, current from the transformer primary winding, so that current draws the more amount of current during the load operation. So at that time some harmonics will be developed. So third harmonics and fifth harmonics, like that all the harmonics are present, but we will consider the effect of the only third harmonics only. Why? Because those harmonics only more severe in the operations of the transformer. Operation of the transformer. So if there is a path for the third harmonic, then there will be losses in the transformer. So here there is no path, so there is no third harmonics in this core type transformer. Core type transformer. And coming to the 5-limbed shell type transformer. So in the shell type transformer, we have 5 limbs. 1, 2, 3, 4, 5 limbs. So winding is surrounded by the core on both sides. So here in the 3 limbs we have made the winding, and 2 limbs are provided for the mechanical support and the for the protection purpose. And outer limbs have the half of the cross sectional area as compared with the inner limbs. So the outer limbs there is no winding, so that's why the cross sectional area of the outer limbs are somewhat less, that means a half when compared with the inner limbs. And similarly the copper requirement is less. Why? Because here in this shell type, as in case of the single phase shell type transformer, we can make the primary winding and then the secondary winding. There is no combination of the on the primary winding we will not provide the secondary winding, beside the primary winding we will provide the secondary winding. So because of that reason there is no increasing of the diameter, so as a result the copper requirement is less but the insulation requirement is more. Why? Because we have to provide the insulation for the primary winding to the core and the secondary winding to the core, not only the secondary winding, LV winding and HV winding, like that. And it is used for the low voltage rating and high current rating. So as we said in the shell type transformer, in case of the single phase transformer, those can be used for the low voltage rating and high current rating. So these are also used for the low voltage rating and high current rating. And there is closed path for the flow of the third harmonic flux, and hence flux is not sinusoidal and hence EMF is not sinusoidal. So here we have the one closed path for the flux generated by this limb, and here we have the closed path for flowing the flux developed at this limb. So for this limb and for this limb we have the one closed path and one closed path. So since we have the closed path, instead of going the flux in this direction, some flux will be going in this direction. So these directions, these fluxes are circulated through this closed path, so there is a effect of the third harmonic. So because of the third harmonic, our flux is not the sinusoidal flux. So because of the sinusoidal, not that is the sinusoidal, so definitely there will be so many losses in our transformer. So but in case of the, if you connect the delta connection, then the delta connected transformer winding itself closed path provides the itself closed path. So the third harmonics are circulating inside the delta winding, so there is no harmonic magnetizing currents can flow, so flux and EMF will be sinusoidal. So there is no circulating of the flux towards the closed path. Those harmonics are present in the inside the delta connection only, so there is no deviation of the sinusoidal nature of our flux. So there is no any losses because of the sinusoidal nature of the flux of the transformer. So next we go for the polarity test of the transformer. So if we want to find the to check the polarity connections of the primary winding and secondary winding, that is either the additive polarity or subtractive polarity, we have to go for the one test. The test is nothing but polarity test. So the setup for the polarity test is as shown in the figure. So here we have the primary winding and here we have the secondary winding. So in between the primary winding and secondary winding we have made the short circuit on one side, and we have connect the one voltmeter and another side. So if the voltmeter reads the sum of the primary and secondary EMF, then the secondary terminals have opposite polarity as compared to the primary terminals. So if you have the additional amount of the primary EMF and secondary EMF, addition of the primary EMF and secondary EMF, then we call it as those two are in opposite polarity, and it is called the series additive polarity. series additive polarity. And similarly, if the voltmeter gives the difference of the primary induced voltage and the secondary induced voltage, then the secondary terminals have the same polarity as compared to the primary terminals. So it is called the series subtractive polarity. So in this manner, we can determine the polarity of the primary winding and secondary winding. So the connections for the three-phase transformers we will see in our next video. Thank you.